So basically students, the electricity and the magnetism was known to us from past 2000 years. We have used the compass needle, which was based on the property of magnetization of the needle and its interaction with the earth's magnetic field, which was used by traders and so many people around that old time when we didn't have any GPS system or what. They just used to that this is north, if we move along north, we will reach the correct direction. So it was obvious that these electricity and magnetism was thought to be two different properties of matter. But accidentally some 200 years ago, the Orested found that the effect of magnet is nothing but the some property of charge itself. Basically, what I want to say is that magnetism is not a different property of matter. Magnetism is the manifestation of another property of magnetic charges. It is another component of the interaction between two charges. Electrostatic force was that component of charges when they are static. But if the charges start moving relative to each other, then apart from electrostatic, one more force acts between them, and that force is called as magnetic force, and that's why we call this thing as magnetic effects of current, because current is nothing but the motion of charges. So the magnetic effect or the magnetic force or the magnetic field is the effect or the property of charge due to its motion. It's quite a unique property. It's quite difficult to see that why the motion of the charge creates a new property. Why just the relative motion between two charges creates a new type of force between them. But it's true. All the magnets around us are nothing but the magnetic effects of current. Even in permanent magnets, the effect is created, the magnetic field is created due to the orbiting electrons around the atom. Each electron orbits around the atom, and each electron creates its own magnetic field. And if we align all the atoms in a given direction, that substance as a whole behaves as a permanent magnet. Generally, but why don't we also have electrons, we also have atoms, but why don't we all behave as magnets? The answer for that thing would be because all the electrons, orbiting electrons or the small magnets inside our body are not aligned in a given direction. They are randomly aligned due to thermal energy or due to their inner molecular structure. That's why the net magnetic moment of most of the substances becomes zero, except some ferromagnetic substances or permanent magnets. So let's see what Orested accidentally observed and what he analyzed from doing further more experiments like this, which laid the foundation of magnetism in physics. So basically, Orested was a teacher. He was teaching to his students something. What he saw was that when a current is switched on in a wire, then a deflection is observed in a compass which was placed near to the current carrying wire. It means, for his surprise, he saw that whenever he switched on the current, he saw the deflection in the compass. Compass was again representative of a magnetic phenomena, and of course this current was the representative of electric current or electricity phenomena. So this phenomena is interacting with magnetism. This was the first step when the scientists started thinking about the linking between electricity and magnetism. Further, he also found that if I increase the current, then the deflection also increases. He also found that if he places the needle near to the current carrying wire, then also deflection increases. Somehow he understood if we decrease the distance, the magnetic effect increases, or the magnetic force on the needle is inversely proportional to the separation. Somehow he got to know from doing experiments. And also he also observed that if I increase the current, the deflection increases. It means the magnetic effect will increase with the increase in the current. And one more important thing what he observed was, if we reverse the direction of current, then the deflection also reverses its direction. It means the forces between the needle and the wire can have both the directions depending on the direction of current in the wire. So these were the few important observations, and he also gave a statement about the deflection of the needle, which is also called as swimming rule or left hand swimmer's rule, same things. So let's write one of his few his observations. So first is, if I is increased, the deflection increases. Second, if the separation between wire and compass is decreased, then also deflection increases. Third, if the direction of current is reversed, then the deflection also gets reversed. So these were the three important observations, and the statement from his observation he gave was about the direction of deflection. So he stated that if we swim along the current carrying wire facing towards it, then the deflection of needle will be towards left hand of swimmer. So it's quite easy. If we move in the direction of current carrying current with facing toward it, means I can swim in, suppose the current is flowing from top to bottom in vertical direction, so I have so many directions to flow along the current. Suppose I can flow like this, I can also flow like this, but I have to make sure that my face I should face towards the current carrying wire. So suppose the current is going from, as I have said, from top to bottom in vertical upward direction, and if I swim along this current, then if I place a compass over here, then the deflection in the needle will be towards my left. So if I want to know what will the deflection of the compass needle due to this current carrying wire at this position, then at this position I will try to swim in the direction of current carrying wire, so the deflection will be towards my left hand, or you can see the deflection will be in this direction. So it's quite simple. For example, even I can also make a diagram. Suppose if this current is flowing in this direction, we have to find what is the deflection in this compass. So if I swim in this direction, so if I swim along this direction, then you can clearly see by facing it, that a deflection towards left hand of the swimmer will be the deflection of the needle. So similarly, we can solve the problems using this statement, but this is not very important. Let's go ahead with the more important things, that is Lenz's law, Lorentz force, and so on.